All right, gotta say, the title of this week's Stitch material is a little intimidating, even for me. Transgressing the boundaries toward a transformative hermeneutics of quantum gravity.
Shoot, it's a mouthful.
It really is. But hey, that's why we do these deep dives, right? To unpack these dense, wild ideas.
Exactly. And trust me, this one is a doozy. But we're going to break it down step by step and see how it all connects. And believe it or not, a good place to start is with something we all experience every single day. Gravity.
Okay, gravity. Seems pretty straightforward, right? What goes up must come down.
That's what we're used to, yeah. But what if I told you that our everyday experience of gravity is just the tip of the iceberg? Einstein's theory of general relativity totally changed how we understand it. Ready for this? Imagine you're holding a bowling ball.
Okay, got it. Holding a bowling ball.
It's not just pulling down. It's actually warping the space and time around it. That warp, that curve, that's gravity.
Hold on. So gravity isn't just a force. It's like bending the fabric of reality itself.
Exactly. Think of space-time like a trampoline. You put a bowling ball on it, the trampoline bends.
Yeah, makes sense.
The ball, that's like a star, a massive object. The trampoline is space-time. And that dip, that curvature the ball creates, that's what causes planets to orbit stars. They're not being pulled, they're following those curves in space-time.
Okay, my mind is already a little blown, but I think I'm starting to get it. So how does this lead to things like black holes or even time travel? And what's it got to do with philosophy? It feels like we're already covering 3 different subjects at once.
That's the beauty of it. They are connected. See, if space-time is flexible enough to bend, it can bend a lot, like a whole lot. Black holes, those are regions where space-time is so warped, so extremely curved, that nothing, not even light, can escape.
Oh, whoa.
Yeah. And time travel, those closed time-like curves Sokal mentions, those are like loops in space-time.
Yeah.
Paths that could theoretically allow you to travel through time.
Time travel. Okay, I'll bite. But philosophy.
Right. So you see, philosophers like Derrida, they were fascinated by how relativity challenged our common sense view of the world.
Derrida. Okay, now that's a name I recognize. Deconstruction, right? But how does that connect to Einstein and bending space-time?
Well, Derrida argued that meaning is fluid, not fixed. Kind of like how Einstein showed that even something as seemingly constant as the speed of light is relative, depending on your frame of reference. There's no single objective truth, just multiple perspectives.
Whoa, okay. So even physics, the study of the fundamental laws of the universe, it's open to interpretation. It's all connected. Man, this is already making me question everything I thought I knew.
That's the first step to understanding the truly mind-blowing world of quantum mechanics.
Quantum mechanics. Okay, gotta admit, this is the part I've been both excited and terrified about. It always seems like something out of a science fiction novel, you know, where things can be in 2 places at once and cats can be both alive and dead.
Yeah, it does have that science fiction vibe, doesn't it? But it's the reality our universe operates on at the smallest level. And one of the key things about quantum mechanics, it just throws our everyday intuition out the window.
So, in the quantum world, what goes up doesn't have to come down. What are the rules here?
Well, imagine a video game where the rules constantly shift, depending on how you play. Yeah. Like you could walk through walls 1 minute, teleport the next, maybe even rewind time. In the quantum world, those sorts of things aren't just possible, they're fundamental. Take the uncertainty principle, for example.
Uncertainty principle. So does that mean we just can't be sure about anything in the quantum world? Is that what it is?
It's not just about our ability to measure things accurately. It's like baked into reality itself. Heisenberg, the physicist who came up with it, he said, "What we observe is not nature itself, but nature exposed to our method of questioning." Basically, just by observing a quantum system, you change it. Yeah. You can know the position of a particle or its momentum, but never both at the same time.
So it's not just that our instruments are flawed or anything. It's like the act of looking changes what we're looking at.
You got it. And it gets weirder. There's this other mind-blowing concept called complementarity. Think about light, right? Sometimes it acts like a wave, other times like a particle. These are totally different descriptions, but they're both true. It just depends on how you choose to observe it.
Hold on, wait. So something can be 2 completely opposite things at the same time? How is that even possible?
It's a fundamental duality in the quantum world. And it's one of the things that makes it so hard to wrap our heads around. Niels Bohr, he put it this way, this is a good one. We are suspended in language in such a way that we cannot say what is up and what is down. Basically, we need multiple perspectives just to begin to understand reality at this scale.
Okay, my head is officially spinning. So if reality is kind of blurry at its core and things can be in multiple states at once, is there any order to the chaos?
That's where the concepts of discontinuity and interconnectedness come in. And trust me, this is where things get really wild.
Discontinuity and interconnectedness.
Yeah.
Okay, yeah, those sound like pretty heavy concepts. I
Yeah.
gotta say, even with all this talk about warping space-time and particles being waves, this is where I start to feel like I'm losing my grip on reality a little bit.
It's understandable. It really is. These are some of the most radical implications of quantum mechanics. Let's start with discontinuity. Imagine you're watching a movie, right? But instead of a smooth flow of frames, it keeps jumping between scenes, skipping over parts of the story. It's kind of like that at the quantum level. Things don't always change smoothly. Sometimes they make these sudden leaps between states, like an electron teleporting between energy levels in an atom, like the universe is playing a cosmic game of hopscotch.
Okay, so instead of a smooth curve, it's more like a staircase with missing steps. I think I get that. But how does everything stay connected if it's always jumping around like that?
That's where interconnectedness comes in. Even though quantum systems can be in these uncertain, discontinuous states, they're still linked together in this profoundly strange way. There's this mind-blowing concept called Bell's theorem that shows how actions here can instantaneously affect things incredibly far away, even across the vastness of space.
Wait, are we talking faster than light communication here? Isn't that supposed to be impossible?
It's not communication in the way we usually think about it. It's more like the universe has these invisible connections woven into its very fabric. When something changes over here, it can instantly influence something over there. Even if there's no physical way for information to travel between them that fast, Einstein called it spooky action at a distance, and even he was baffled by it.
Spooky is right. It's like the universe is playing this cosmic game of strings where each particle is connected to every other particle by an invisible thread. This is making my head spin almost as much as that whole warping space-time thing.
And you know what? That image of the universe as this vast interconnected web, it's surprisingly accurate. It leads us to the ultimate frontier of physics, quantum gravity. This is where we try to bring together the mind-bending world of quantum mechanics with the equally mind-bending world of general relativity.
Okay, so we're talking about combining the weirdness of the very small with the weirdness of the very large.
Yeah,
Fasten your seatbelts, folks, because I have a feeling things are about to get really wild.
it's true. It's where things get really interesting. Trying to merge these two, quantum mechanics and general relativity, it's like trying to describe a rainbow to someone who's only ever seen black and white.
And not just seeing black and white, but thinking that black and white are the only possibilities.
Exactly. It's a challenge, even for the most brilliant minds in physics. Physicists have been trying to picture what this quantum gravity would look like. Some early attempts used the metaphor of space-time foam. Imagine the fabric of space-time bubbling and churning at the smallest scales, filled with tiny wormholes and black holes popping in and out of existence.
So, not exactly a smooth surface, more like a quantum sea with waves crashing all around us.
That's a great way to put it. And then you got string theory, which got a lot of attention in the physics world. It proposes that everything in the universe, every particle and every force, is made up of these tiny vibrating strings. And get this, these strings vibrate in different dimensions, most of which are curled up and hidden from our perception. What we experience as space-time is just the large-scale projection of these vibrating strings.
Whoa, okay, so it's like the universe is this giant guitar string and the way it vibrates determines everything we see and experience. Is that what string theory is saying?
You got it. But there's a catch.
Hmm.
The math behind string theory is so complex that for now, it remains largely theoretical. It's incredibly difficult to test its predictions with current technology.
So it's a beautiful idea, but still a work in progress. Are there any other contenders in this race to explain quantum gravity?
There are. Some physicists are exploring the idea of a space-time weave, where the universe is like a giant tapestry woven from interconnected threads of quantum information. And then there's a even more radical notion of a morphogenetic field.
A morpho what now? That sounds like something straight out of a biology textbook.
It does, doesn't it?
Yeah.
The morphogenetic field is this concept borrowed from developmental biology. It's the idea that there's this field that guides the development of form and patterns in living organisms. But some physicists speculate that a similar field might exist on a cosmic scale, influencing the structure and evolution of the universe itself.
Hold on, so you're saying that the same force that shapes a flower or a human embryo could be responsible for the large-scale structure of galaxies and the laws of physics themselves?
It sounds incredible, but it's a possibility that some physicists are seriously considering. And if true, it would mean that the universe is even more interconnected than we ever imagined, with information flowing between all levels of reality, from the smallest particles to the largest structures.
Wow, that's just wow. Okay, so we've got Foam, strings, weaves, and now fields that can shape the universe from the bottom up. My brain is officially fried. So, what does this all mean after this incredible journey through the frontiers of physics? What are the key takeaways?
It means that the universe is far stranger, more mysterious, and more interconnected than we ever imagined. It means that our everyday experience of reality is just a tiny sliver of a much grander, more mind-bending picture. And it means that the quest to understand the universe is ultimately a quest to understand ourselves and our place within this vast, interconnected web of existence.
That's a pretty profound thought to end on. I think we've all got some serious pondering to do after this one. So until next time, keep looking up at the stars, keep asking the big questions, and keep exploring the universe within and around you.